There's a picture we've all carried in our heads for decades, isn't there? When you think about finding alien life, you probably imagine a vast red desert stretching to a dusty horizon, maybe with a faded blue sky overhead. You picture rovers crawling over rocks, digging for ancient riverbeds, listening for whispers of water that once flowed. We've sent our best and brightest, our most advanced machines to Mars. We've studied its canyons, its polar caps, its tantalizing traces of a wetter past, all in pursuit of one of the most profound questions humanity has ever asked. Are we alone? For so long, Mars was the answer, or at least the most promising place to start. It was close. We could see it with our telescopes, then with our probes. We saw evidence of water, which, to us, meant life. But what if we were looking in the wrong place entirely? What if the universe, in its boundless, beautiful strangeness, had a secret up its sleeve that defied all our desert-bound expectations? Forget the passive game of listening for faint radio signals from stars light years away. That's like dropping a message in a bottle into an infinite ocean and hoping it washes up on an alien shore. The real search for alien life, the active, aggressive, pioneering hunt, isn't about waiting. It's about drilling. It's about breaking through miles of alien ice, not to reach a sunlit, familiar world, but to plunge into an ocean that has never seen the light of day. An ocean hidden, vast, and potentially teeming with life, right here in our own cosmic neighborhood. This isn't a story of dusty red plains and ancient riverbeds. This is a story of two utterly alien worlds, shrouded in mystery, where the most tantalizing promise of extraterrestrial life doesn't lie on the surface, but deep beneath. It's a paradigm shift, a cosmic aha moment that turns everything we thought we knew about the search for life on its head. We're not looking for the wrong kind of desert anymore. We're looking for the right kind of ocean. Imagine, if you will, a world utterly encased in ice. Not just a thin sheet, but a shell tens of miles thick, a colossal frozen shield. Beneath that shield, in perpetual darkness, lies an ocean of liquid saltwater, vast beyond measure, warmed by forces we barely comprehend. And in that dark, deep sea, the very ingredients for life, the building blocks, the energy, the liquid water itself, might be swirling, evolving, perhaps even thriving. This isn't science fiction anymore. This is the new frontier of astrobiology, the ocean worlds of Europa and Enceladus. For centuries, our gaze was fixed on the planets. Mars, Venus, the gas giants. They were the grand stages of our solar system. We observed them, theorized about them, and eventually sent our robotic envoys to touch their surfaces. And Mars, our rusty neighbor, captivated us most of all. Its polar ice caps waxed and waned with the seasons. Its surface was scarred with channels that looked eerily like dried-up rivers, and its thin atmosphere hinted at a warmer, wetter past. It was intuitive. Life on Earth thrives with water and sunlight. So, logically, we sought those same conditions elsewhere. If Mars once had flowing water, perhaps it had life. If not now, then in its ancient past. The allure was undeniable, the mission clear. We sent Viking in the 70s, then Pathfinder, Spirit, Opportunity, Curiosity, and Perseverance, each more sophisticated than the last, all designed to scour the Martian landscape for the faintest whisper of biology. And they found incredible things, evidence of ancient lakes, river deltas, minerals that form only in the presence of water. Mars was indeed a watery world billions of years ago. But the planet itself is a desert now, exposed to the harsh radiation of space, its thin atmosphere unable to hold on to liquid water for long. Any life that might have existed would have gone deep underground, or adapted to extreme conditions, or simply vanished. The search became one of archaeology, of looking for fossils, for echoes of a bygone era. It was a noble pursuit, and one that continues to yield fascinating insights into planetary evolution. But the focus was always on the surface, or just beneath it, of a world fundamentally shaped by the sun. Then, slowly, subtly, the paradigm began to shift. It started not with a new mission to Mars, but with distant probes venturing into the outer reaches of our solar system, to the gas giants and their many moons. These were worlds previously dismissed as too cold, too far from the sun's life-giving warmth. Frozen, inert spheres, we thought. But the universe, as it often does, had a surprise waiting for us. The first hint of this profound shift came from a moon of Jupiter, a world named Europa. Discovered by Galileo Galilei himself in 1610, along with Jupiter's other large moons, Europa was initially just another point of light in the vast cosmic tapestry. For centuries, it remained a scientific curiosity, a small, icy orb orbiting the largest planet in our solar system. But then came the Voyager spacecraft in the 1970s, making humanity's first close-up flybys. What they revealed was astounding. Europa wasn't a heavily cratered, ancient world like our own moon. Instead, it was remarkably smooth, crisscrossed with intricate lines and fractures, almost like a cracked eggshell. This suggested a young, active surface, constantly being reshaped, and that, in turn, hinted at something dynamic happening beneath. But it was NASA's Galileo mission, orbiting Jupiter from 1995 to 2003, that truly began to pull back the icy curtain on Europa's secret. Galileo carried a suite of instruments, one of the most crucial being its magnetometer. This device measures magnetic fields. As Galileo swooped past Europa, it detected something unexpected, a distorted magnetic field around the moon. This wasn't Europa's own magnetic field, but one induced by Jupiter's incredibly powerful magnetosphere. And for a magnetic field to be induced like that, there had to be something electrically conductive beneath Europa's surface. What could be electrically conductive and globally present? A vast ocean of salty liquid water. Imagine the moment of realization for the scientists poring over that data. Dr. Margaret Keevelson, a key scientist on the Galileo mission, and her team used these subtle magnetometer readings to infer the existence of this hidden salty ocean. It was a detective story, a scientific cold case, being solved across millions of miles of space. The evidence wasn't direct, no dramatic geysers yet, but it was compelling, almost undeniable. Europa, this seemingly frozen world, held more liquid water than all of Earth's oceans combined, tucked away beneath an ice shell, estimated to be 10 to 30 kilometers, 6 to 20 miles, thick. The ocean itself could be up to 100 kilometers, 60 miles deep. This wasn't just a puddle. It was a global deep-sea realm, a vast hidden continent of water. But how could such an ocean remain liquid so far from the sun? This is where the universe reveals another one of its elegant, powerful tricks: tidal heating. Imagine taking a rubber ball and constantly squeezing and stretching it. That friction, that deformation, generates heat. Now, imagine Jupiter, a giant among planets, exerting an immense gravitational pull on Europa. As Europa orbits Jupiter, and as it interacts gravitationally with its neighboring moons, Io and Ganymede, it gets caught in a cosmic tug-of-war. Jupiter's gravity is not uniform across Europa. The side closer to Jupiter feels a stronger pull than the side farther away. This differential gravity constantly flexes and kneads Europa's interior, causing friction and generating immense heat. It's this continuous gravitational squeezing and stretching, tidal heating, that keeps Europa's vast subsurface ocean liquid, preventing it from freezing solid. So, here we had it, liquid water, kept warm by an internal engine, protected from the harsh radiation of space by a miles-thick ice shell. The fundamental ingredient for life as we know it, flourishing in a place no one had seriously considered a prime candidate just decades before. The idea of looking for life in a sunlit desert began to feel, well, a little limited. The most promising place for life might not be where the sun shines brightest, but where internal forces churn and warm a hidden sea. But Europa was just the beginning. The universe had another, even more dramatic revelation waiting for us. This time around Saturn, another ringed titan of our solar system. Enter Enceladus, a much smaller moon, a mere speck compared to Europa, but one that would soon scream its secrets to the cosmos. The Cassini-Huygens mission, a joint effort by NASA, ESA, and ASI, arrived at Saturn in 2004 and spent 13 glorious years orbiting the gas giant, exploring its rings and moons. And it was Cassini that stumbled upon the most astonishing discovery of all. In 2005, instruments on Cassini detected a strange disturbance in Saturn's magnetic field near Enceladus. Then images revealed something incredible. Geysers, plumes of water vapor and ice grains, were erupting dramatically from the moon's south pole, shooting hundreds of kilometers into space like colossal cosmic fountains. This wasn't an inference, a subtle magnetic anomaly. This was direct, undeniable evidence. Enceladus was actively venting material from its interior into space. It was direct conduit, a cosmic pipeline, to whatever lay beneath its icy crust. Dr. Carolyn Porco, leader of the Cassini imaging science team, vividly described the eureka moment of realizing they weren't just seeing an atmosphere, but actively flying through an eruption from a hidden ocean. The Cassini mission then did something truly audacious. It flew through those plumes again and again, like a scientific dragon hunter tasting the breath of its quarry. Its instruments, particularly the ion and neutral mass spectrometer, INMS, acted like a cosmic tongue, tasting the composition of the material being ejected. And what it tasted was extraordinary. Saltwater, organic compounds, the complex carbon-based molecules that are the very stuff of life, and even silica nanoparticles. Silica, you might ask. Why is that important? On Earth, silica is formed when hot water interacts with rock. Its presence in Enceladus's plumes was a smoking gun for active hydrothermal vents on the moon's ocean floor. Imagine the deep-sea vents on Earth, spewing superheated mineral-rich water from cracks in the seafloor, creating vibrant ecosystems entirely independent of sunlight. These black smokers are thought by many to be where life on Earth may have first begun. And Cassini was telling us that Enceladus had them too. The discoveries didn't stop there. Further analysis of the plume data by Cassini revealed molecular hydrogen, another key indicator of water-rock interactions and a potential energy source for microbes. Then, in a truly monumental discovery announced in June 2023, scientists confirmed the detection of phosphorus in Enceladus's plumes. This was a game-changer. Phosphorus is the last of the 6 essential elements for life, as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, schnaps, to be confirmed in Enceladus's ocean. It means that this small dynamic moon has all the fundamental chemical building blocks for life, along with liquid water and an energy source. The phosphate concentrations in Enceladus's ocean are even estimated to be at least 100 times higher than in Earth's oceans, a surprising abundance for this life-critical element. And just to add another layer of intrigue, Enceladus's ocean is alkaline, with a pH similar to soapy water. Now it's worth noting that recent research, as of late 2025, has introduced a fascinating nuance to the story of Enceladus's organics. Some laboratory experiments suggest that certain organic molecules detected in the plumes might also be formed by radiation hitting the surface ice, rather than exclusively originating from the subsurface ocean. This doesn't diminish Enceladus's habitability potential, but it adds a layer of complexity to our cosmic detective work. Scientists must now learn to distinguish between radiation-made organics and those born in a subsurface sea. However, fresh analysis of Cassini data continues to reveal new complex organic molecules, strengthening the case for complex chemical reactions taking place within its underground ocean, some of which could be precursors to amino acids, the building blocks of proteins. This ongoing scientific dialogue only deepens the mystery and the excitement surrounding this remarkable moon. So we have two worlds: Europa, a massive, older, and more mysterious giant with a hidden ocean hinted at by subtle magnetic clues, and Enceladus, a smaller, dynamic, and actively revealing moon that is screaming its secrets to the cosmos. Both are powered by the relentless gravitational dance of their host planets, Jupiter and Saturn, keeping their internal oceans warm and liquid through tidal heating. And both possess the key ingredients that, on Earth, led to life. This is the profound shift. For generations we peered at the night sky, hoping for a signal, a flash, a sign from a distant sunlit world. We spent decades looking for life on arid red deserts, convinced that liquid water could only exist where the sun warmed the surface. But the universe, in its infinite creativity, hides its most tantalizing secrets not in the light, but in the deep, in the dark, beneath miles of alien ice. The most promising place to find extraterrestrial life isn't a sunlit world at all, but an ocean that has been in total profound darkness for billions of years, waiting for us to find it. The Europa Clipper mission, for instance, launched on October 14, 2024, on a journey that will take it to Jupiter in April 2030. It won't land, not yet. Instead, it will perform approximately 49 close flybys of Europa, sometimes swooping as low as 25 kilometers, 16 miles, above the surface. Europa Clipper is equipped with an incredible suite of instruments designed to X-ray the moon from orbit. It carries the radar for Europa assessment and sounding, ocean to near surface, or reason, an ice-penetrating radar that will peer through the ice shell, mapping its structure and searching for pockets of liquid water, or even the ice-ocean interface itself, up to 30 kilometers deep. The Europa Clipper magnetometer, ECM, and the plasma instrument for magnetic sounding, PIMS, will work in tandem to precisely measure Europa's induced magnetic field, refining our understanding of the ocean's depth, salinity, and the ice shell's thickness. Cameras like the Europa Imaging System, EIS, will capture stunning high-resolution images, while spectrometers like the Mapping Imaging Spectrometer for Europa, MIC, will map the surface composition, searching for salts, organics, and even signs of recent plumes. These missions are not just about scientific data. They are about preparing for the next, even bolder steps. Because the ultimate goal isn't just to detect these oceans, but to explore them. Imagine a future mission, a lander touching down gently on Europa's frozen surface. Then, from its belly, a cryobot emerges, a sophisticated nuclear-powered probe designed to melt its way through miles of solid ice. This isn't a quick trip. It's a slow, deliberate descent, potentially taking years, battling immense pressure and absolute darkness. But the image, the potential is breathtaking. A probe finally breaking through the last few meters of ice, plunging into the vast, dark, liquid saltwater ocean below. And what then? Autonomous submarines, equipped with advanced sensors and cameras, could be released, silently navigating these sunless alien seas. They would explore hydrothermal vents, search for microbial ecosystems, and swim through water that has never felt the touch of sunlight. The engineering challenges are immense, almost beyond our current capabilities. But the vision is clear: to actively, aggressively, and directly search for life in these hidden sanctuaries. This is the true frontier of the search for alien life. It's a journey not to a distant star, but to worlds in our own backyard, worlds that challenge our assumptions and expand our understanding of where and how life can thrive. It is a testament to human ingenuity and our insatiable curiosity, a quest that could fundamentally reshape our understanding of our place in the universe. If we find microbes there, flourishing in the perpetual night of an alien ocean, what does that mean for us? What does it mean for the very definition of life and for our singular existence on this pale blue dot? The answer, like the oceans themselves, lies hidden, waiting to be discovered. We just talked about a future that feels almost like science fiction, a future where humanity drills through miles of alien ice and sends submarines to explore oceans that have never seen the light of day. But before we can even dream of such incredible journeys, we had to know those oceans were there. We had to find the proof. And for decades, the most tantalizing, the most compelling proof of life's hidden sanctuaries came from a world orbiting Jupiter, a moon named Europa. The story of its secret ocean is a testament to human ingenuity, a cosmic detective story solved not by direct observation, but by listening to the silent, invisible pulse of a sleeping giant. Imagine for a moment the year 1610. A man named Galileo Galilei, with a crude telescope he built himself, turns his gaze skyward. He sees Jupiter, and around it, 4 tiny points of light, dancing in a celestial ballet. He realizes, with a jolt that would shake the foundations of human thought, that these are moons, orbiting another planet. It's a discovery that helps pry open the rigid grip of the geocentric model, changing our understanding of the cosmos forever. One of those moons, a small, icy world, he named Europa. For centuries, it remained just a speck of light, a cold, distant world, its secrets locked away. Fast forward to the 1970s. The twin Voyager spacecraft, humanity's intrepid scouts, made their close-up flybys of Jupiter, giving us our first real glimpse of Europa. What they saw was extraordinary. A strikingly smooth surface, crisscrossed with intricate lines and cracks, yet remarkably few craters. This wasn't the pockmarked face of a dead world. This was a young, geologically active surface. And what could be making it so active, so smooth? The scientists began to whisper a radical idea. Perhaps something was moving beneath that icy crust, something liquid, something that could resurface the moon and erase the scars of cosmic impacts. But a whisper isn't proof. It wasn't until the mid-1990s, when NASA's Galileo mission arrived at Jupiter, that the whispers began to solidify into scientific theory. Galileo, a truly groundbreaking spacecraft, spent 8 years orbiting the gas giant, from 1995 to 2003, meticulously studying Jupiter and its entourage of moons. And it was Galileo that brought us the first truly compelling evidence that Europa wasn't just an icy rock, but a world with a vast hidden ocean. This is where the story gets really interesting, because Galileo didn't see the ocean. No camera could peer through miles of solid ice. Instead, Galileo used an invisible force to reveal an invisible world. Think of it like a doctor using an MRI. When you go in for an MRI, the machine doesn't cut you open to see inside. Instead, it uses powerful magnets and radio waves to create a detailed map of the soft tissues and fluids inside your body. It detects tiny shifts and echoes in magnetic fields that reveal what's hidden beneath your skin. In a surprisingly similar way, scientists on the Galileo mission used the spacecraft's magnetometer, an instrument designed to measure magnetic fields, to see inside Europa. Jupiter itself is a magnetic powerhouse, generating an incredibly strong magnetic field that permeates its entire system, including its moons. As Europa orbits Jupiter, it's constantly bathed in this powerful magnetic energy. Now, if Europa were just a solid ball of ice and rock, Jupiter's magnetic field would simply pass through it, largely undisturbed. But what Galileo's magnetometer detected was something else entirely. It detected a distortion in Jupiter's magnetic field, a subtle but unmistakable warp in the force field around Europa. Imagine a river flowing steadily, and then suddenly the current slows, eddies form, and the water around a hidden obstacle begins to swirl in a different direction. That's what Galileo saw in Jupiter's magnetic field as it encountered Europa. This wasn't just a random fluctuation. It was a rhythmic, induced magnetic field, changing precisely with Europa's orbit around Jupiter. And there's only one thing in the universe that can create such a distinct magnetic signature: a global ocean of salty, electrically conductive water sloshing around beneath the surface. Think about it. Salt water conducts electricity. As Jupiter's immense magnetic field sweeps past Europa, it induces electrical currents within this vast subsurface saltwater ocean. These electrical currents, in turn, generate their own secondary magnetic field. It's this secondary induced magnetic field that Galileo detected. It was like feeling the subtle rhythmic pulse of a sleeping giant, a pulse created by the movement of an ocean that had never seen the light of day. The implications were staggering. This wasn't just a puddle. This was an ocean of truly colossal proportions. Scientists estimate that Europa's subsurface ocean contains 2 to 3 times the volume of all of Earth's oceans combined. Twice the water of every ocean, every sea, every lake, every river on our home planet, all hidden beneath a shell of ice that's estimated to be anywhere from 10 to 30 kilometers thick. And beneath that immense ice shell, the ocean itself could be up to 100 kilometers deep. Just try to wrap your mind around that scale. We're talking about a world of water, so vast, so deep, that it dwarfs anything we know on Earth. But how could an ocean possibly remain liquid, so far from the sun, where temperatures plummet to hundreds of degrees below zero? This is where the physics of tidal heating comes into play, a concept that is both elegant and incredibly powerful. Europa isn't alone in its orbit around Jupiter. It's locked in a gravitational dance with its larger siblings, Io and Ganymede, and with Jupiter itself. This cosmic tug-of-war, this constant gravitational squeezing and stretching, flexes and kneads Europa's interior. Imagine constantly bending a paperclip back and forth. Eventually it gets warm. The same principle applies to Europa, but on a planetary scale. This immense internal friction generates enough heat to keep that vast ocean liquid, preventing it from freezing solid, even in the frigid depths of space. The team behind Galileo, particularly scientists like Dr. Margaret Kivelson, meticulously analyzed this magnetic data. It was a painstaking process, requiring incredible scientific rigor and a deep understanding of planetary physics. Their work provided the bedrock for our current understanding of Europa, transforming it from a mere icy moon into one of the most compelling candidates for extraterrestrial life in our solar system. Their ingenuity allowed us to see what was utterly invisible, to hear the silent song of a hidden sea, and the story of Europa continues to unfold. Even decades after Galileo ended its mission, its data is still yielding secrets. In 2018, scientists reanalyzed some of that old Galileo data, applying modern techniques, and found new evidence hinting that Europa might even have its own plumes of water erupting from its surface, similar to what we've seen on another ocean world. It's like a scientific cold case being solved, where old clues, looked at with fresh eyes, reveal a deeper truth. It suggests that Galileo might have, unknowingly, even flown through one of these plumes back in 1997. So, Europa stands today as a massive, older, and more mysterious giant, its secrets hinted at by subtle, indirect clues. It's a world that forces us to redefine what a habitable environment can look like. No sunlight, no atmosphere to speak of, yet beneath its frozen shell, a warm, salty ocean brimming with potential. This sleeping giant, with its magnetic pulse, offered the first undeniable whisper that the universe might be far wetter and far more alive than we ever dared to imagine. It set the stage for the next incredible discovery, one that would not only confirm the existence of alien oceans, but would let us actually taste them. It's like a scientific cold case being solved, where old clues, looked at with fresh eyes, reveal a deeper truth. It suggests that Galileo might have, unknowingly, even flown through one of these plumes back in 1997. So, Europa stands today as a massive, older, and more mysterious giant, its secrets hinted at by subtle, indirect clues. It's a world that forces us to redefine what a habitable environment can look like. No sunlight, no atmosphere to speak of, yet beneath its frozen shell, a warm, salty ocean, brimming with potential. This sleeping giant, with its magnetic pulse, offered the first undeniable whisper that the universe might be far wetter and far more alive than we ever dared to imagine. It set the stage for the next incredible discovery, one that would not only confirm the existence of alien oceans, but would let us actually taste them. But before we dive into that incredible journey, there's a fundamental question we have to grapple with, a puzzle that might seem counterintuitive at first glance. How can a world so far from the sun, a world where the surface temperature hovers around a frigid negative 260 degrees Fahrenheit, possibly harbor a vast liquid ocean? We're talking about an ocean estimated to contain 2 to 3 times the volume of all of Earth's oceans combined, hidden beneath an ice shell 10 to 30 kilometers thick, with the ocean itself potentially reaching depths of 100 kilometers. That's a lot of water and a lot of ice in a very cold place. The answer, it turns out, is one of the universe's most elegant and surprising tricks, a testament to the fact that life-giving energy doesn't always come in the form of sunlight. It can come from something far more primal, far more universal: the sheer relentless force of gravity. Now, I want you to imagine something with me. Pick up a metal paperclip. Go ahead, I'll wait. Got it? Good. Now, take that paperclip and bend it back and forth. Bend it, straighten it, bend it again. Keep doing it over and over. What do you feel? If you do it enough, that little piece of metal starts to get warm, right? Maybe even hot to the touch. It's a simple, everyday phenomenon, one you might have experienced without ever really thinking about why it happens. This isn't magic, it's physics. As you bend the paperclip, you're causing internal friction within the metal. The molecules inside are rubbing against each other, resisting that constant deformation. That resistance, that friction, converts the mechanical energy of your bending hand into thermal energy, into heat. The more you bend it, the more friction you create, and the hotter the paperclip becomes. It's a neat little demonstration of energy conversion, happening right there in your fingers. Now hold that thought about the bending paperclip, about the internal friction. and about the heat it generates. Because that simple act, that everyday experience, is the key to understanding how Europa and other ocean worlds like it manage to maintain vast liquid oceans beneath miles of ice, billions of miles from the comforting warmth of our sun. Imagine, if you will, that Europa is that paperclip, and the hand bending it, the immense unseen force causing that constant flex and strain, is none other than Jupiter itself. Jupiter, the king of our solar system, is a truly colossal planet. Its mass is more than twice that of all the other planets combined. It's a gravitational behemoth, exerting an incredible pull on everything around it, especially its largest moons. Europa is one of these, locked in a magnificent perpetual dance with Jupiter and its neighboring Jovian moons, Io and Ganymede. This cosmic ballet is what gives rise to the phenomenon we call tidal heating. Here's how it works. Europa doesn't orbit Jupiter in a perfect circle. Its orbit is slightly elliptical, or egg-shaped. As Europa swings closer to Jupiter, the giant planet's gravitational pull on the moon intensifies, stretching Europa more strongly. Think of it like a cosmic tug-of-war. Jupiter's gravity tries to pull Europa apart, elongating it along an axis pointing towards the gas giant. Then, as Europa swings further away in its orbit, Jupiter's gravitational grip loosens slightly, and the moon relaxes back into a more spherical shape. This isn't just a gentle wobble. This is a constant, rhythmic stretching and squeezing, a perpetual kneading of Europa's entire body. The gravitational forces from Jupiter, combined with the resonant gravitational interactions with its sibling moons Io and Ganymede, keep Europa's orbit from circularizing. This means that Europa is continuously being pulled and released, pulled and released. It's like Jupiter is taking Europa in its giant hands and just flexing it over and over again. For billions of years, just like our paperclip, this constant flexing generates immense internal friction within Europa's rocky interior. This friction, this resistance to the endless deformation, produces a tremendous amount of heat. This isn't external heat from the sun. It's heat generated from within the moon itself. It's an internal furnace, stoked by the inexorable pull of Jupiter's gravity. This tidal heating is the primary mechanism keeping these subsurface oceans liquid, far from the sun's warmth. And this, my friends, is the aha moment. The sun is not the only source of life-giving energy. Sheer gravitational force can create a warm, stable, and potentially habitable environment. It's a profound shift in perspective, one that completely rewrites our understanding of where life might be found in the cosmos. For decades, when we thought about habitable zones, we drew neat little circles around stars, marking off the region where liquid water could exist on a planet's surface. But tidal heating shatters that assumption, opening up entirely new realms, pushing the boundaries of habitability far beyond what we ever imagined. This internal heat doesn't just keep the ocean liquid, it does something even more exciting. It drives geological activity on Europa's rocky seafloor. Imagine the floor of Europa's ocean, miles beneath the ice. Here, the heat generated by tidal forces can cause water to percolate through the moon's rocky core, heating up and dissolving minerals. This superheated, chemically rich water then erupts back into the ocean through vents on the seafloor, what we call hydrothermal vents. On Earth, these hydrothermal vents, often found along mid-ocean ridges, are vibrant oases of life, teeming with unique ecosystems that thrive in the absence of sunlight. They are powered by chemosynthesis, where microbes derive energy from chemical reactions with the superheated, mineral-rich fluids emerging from the vents. Many scientists believe that these very same types of hydrothermal vents may have been the cradle for life on Earth, providing the energy and chemical building blocks necessary for the first organisms to emerge. If tidal heating is creating similar environments on Europa, then the implications are staggering. We could be looking at a world not only with liquid water, but with the entire energy system that supported life's genesis here, on our own planet. The evidence for this hidden dynamic world on Europa didn't come easily. Remember the Galileo spacecraft? It was NASA's intrepid explorer orbiting Jupiter from 1995 to 2003. Its primary mission wasn't to search for oceans, but to study Jupiter and its moons in detail. Yet, it was Galileo's magnetometer, an instrument designed to measure magnetic fields that provided the crucial indirect evidence for Europa's subsurface ocean. Dr. Margaret Keivelson, a brilliant scientist on the Galileo mission, led the team that made this pivotal discovery. As Galileo swooped past Europa, its magnetometer detected something extraordinary: a distorted magnetic field around the moon. This wasn't Europa's own magnetic field, as Europa doesn't have one in the same way Earth does. Instead, it was an induced magnetic field, caused by Jupiter's powerful magnetic field interacting with something electrically conductive beneath Europa's icy crust. The only thing that could explain such a strong induced magnetic field was a global ocean of salty, electrically conductive water. It was like a cosmic X-ray, allowing us to see a hidden ocean simply by observing its magnetic signature. Before Galileo, our views of Europa were shaped by the twin Voyager spacecraft in the 1970s. These pioneering probes gave us the first close-up images of Europa, revealing a surprisingly smooth surface with very few craters. This lack of craters was a huge clue. On airless bodies in the solar system, craters accumulate over billions of years. A surface with few craters suggests a young, active geology, meaning something has been resurfacing the moon, erasing the cosmic pockmarks. That something was hypothesized to be liquid water, interacting with the ice, constantly refreshing the surface. Voyager provided the hint, but Galileo gave us the magnetic proof. The story of Europa is one of slow, painstaking scientific detective work, a testament to human perseverance. From Galileo Galilei's initial discovery of the moon in 1610, which helped dismantle the geocentric model of the universe, to the Voyager probe's tantalizing hints, and finally to the Galileo spacecraft's magnetic revelations, each step brought us closer to this incredible truth. And even after Galileo's mission ended, scientists continued to pore over its data. The reanalysis in 2018, finding new evidence for plumes on Europa by looking at 20-year-old magnetic field data, perfectly illustrates this cold case approach. It's a powerful reminder that sometimes the answers we seek have been right in front of us all along, waiting for the right tools or the right perspective to be revealed. So, Europa remains a world of immense, quiet mystery. Its massive, deep ocean, kept warm by the relentless gravitational dance with Jupiter, represents a prime candidate for life. It's a world where the sun's light never penetrates, a realm of eternal darkness that could, paradoxically, be teeming with life. Its ice shell, a barrier both formidable and protective, safeguards this potential sanctuary from the harsh radiation of Jupiter. But how do we go beyond these tantalizing clues? How do we move from inference to direct observation? That's where the next generation of explorers comes in. NASA's Europa Clipper mission, launched in October 2024, is designed to perform a detailed reconnaissance of Europa, specifically to investigate its habitability. This incredible spacecraft will perform approximately 49 close flybys of Europa, dipping to altitudes as low as 25 kilometers, essentially X-raying the moon from orbit. Europa Clipper will carry a suite of advanced instruments, each one a technological marvel designed to peer through Europa's icy veil. It will have an ice-penetrating radar, which will send radio waves deep into the ice shell to map its thickness and search for pockets of liquid water within the ice itself. It will carry an even more sensitive magnetometer, building on Galileo's legacy, to better characterize the ocean's properties. It will have cameras to map the surface in unprecedented detail, looking for active plumes or signs of recent geological activity. And it will have spectrometers to analyze the composition of any material ejected from the subsurface, giving us clues about the ocean's chemistry. The Europa Clipper mission is our most ambitious step yet to confirm the presence of Europa's ocean and assess its potential for life. It's the bridge between Galileo's whispers and a future where we might, one day, actually send a probe to melt its way through miles of ice and explore those dark alien seas firsthand. It's an active, aggressive search, driven by the profound question, are we alone? The discovery of tidal heating fundamentally changed the game. It showed us that habitability isn't just about a star's light, but about the intricate, powerful dance of gravity. It revealed a hidden engine, a cosmic furnace capable of sustaining vast, warm oceans in the most unexpected corners of our solar system. This insight not only strengthens the case for life on Europa, but it expands our imagination to countless other icy moons and rogue planets throughout the galaxy. Worlds that might harbor similar hidden sanctuaries, powered not by starlight, but by the ceaseless internal friction of their own making. It was this paradigm shift, this understanding of gravity's life-giving power, that prepared us for the next, even more dramatic chapter in our search. A chapter written on a much smaller, yet far more vocal moon. A moon that didn't just hint at an ocean, but actively cried out its secrets to the cosmos. A moon that didn't just hint at an ocean, but actively cried out its secrets to the cosmos. Imagine for a moment the year 2005. Our faithful Cassini spacecraft, a marvel of human engineering, had settled into orbit around Saturn, that ringed jewel of our outer solar system. For years, we'd been captivated by its majesty, its swirling storms, and its dizzying array of moons. Among them was Enceladus, a relatively tiny, unassuming orb, barely 310 miles across. It looked, frankly, like nothing special, just another frozen snowball, reflecting sunlight with an almost blinding brilliance. Scientists had a passing interest in it, sure, but nobody expected it to become a superstar in the search for extraterrestrial life. But Enceladus, it turned out, was not content to be just another icy face in the crowd. This moon wasn't guarding its secrets. It was actively shouting them into space. The first hint came as Cassini performed a series of close flybys. Dr. Carolyn Porco, the formidable leader of the Cassini imaging science team, and her colleagues were poring over the data, meticulously examining every pixel. And then, they saw it. Not a subtle magnetic anomaly, like the initial clues from Europa, but something far more dramatic, something undeniable. From the south pole of Enceladus, great plumes of water vapor and icy particles were erupting into space. Not a gentle mist, mind you, but active geyser-like jets, spewing material hundreds of miles above the moon's surface. This wasn't a whisper. It was a cosmic cry. The scientific community was stunned. What they had once thought was a static, dead world was, in fact, incredibly dynamic. These weren't ancient eruptions, long since frozen. These were happening right now. The images were breathtaking, almost unbelievable. It was like watching Old Faithful, but on an alien moon, powered by forces we were only just beginning to comprehend. The south pole of Enceladus was marked by strange parallel linear features, which scientists quickly dubbed tiger stripes. These aren't just pretty markings. They are deep, active fissures, the very vents through which the moon was exhaling its hidden world. This discovery didn't just change our understanding of Enceladus. It fundamentally altered the entire astrobiological landscape. Suddenly, this little ice ball, a mere curiosity moments before, became a primary target in our quest to answer the universe's most profound question. Are we alone? The immediate, urgent question was, what exactly was in those plumes? What was Enceladus shouting about? This wasn't a passive game of chance, listening for distant signals. This was active, aggressive, and much closer to home. We didn't have to figure out how to get to the ocean. The ocean came to us. The plumes were a free sample, a direct message from a hidden world, offering itself up for study. And Cassini, with its sophisticated array of instruments, was perfectly positioned to take a taste. Over the next several years, Cassini performed multiple daring fly-throughs directly through these plumes. Imagine that, flying a multi-billion-dollar spacecraft through a cosmic snowstorm erupting from an alien moon. Each pass was a high-stakes gamble, but the payoff was immense. As Cassini sliced through the icy exhalations, its instruments, like cosmic tongues, began to taste the contents of this hidden ocean. What it found was nothing short of revolutionary. The very first analyses confirmed the plumes were indeed made mostly of water vapor and ice grains. But as the data poured in, it revealed a much richer, far more compelling story. Cassini detected not just water, but salt water. This wasn't just frozen vapor. It was material from a vast subsurface ocean, just like the one hypothesized on Europa. But the story got even better. Cassini also found a rich cocktail of organic compounds, the building blocks of life as we know it. These aren't necessarily signs of life itself, but they are the raw ingredients, the carbon-based molecules that form amino acids, proteins, and eventually us. The presence of these complex organics was a huge clue, suggesting a chemistry far more advanced than anyone had dared to hope for. Then came the truly startling discovery: silica nanoparticles. Now, silica might sound mundane, like sand or glass, but on Enceladus, its presence was a smoking gun. On Earth, these tiny silica particles are formed when hot, chemically rich water circulates through rocky seafloors. Think of the black smokers and white smokers at the bottom of our own oceans. Hydrothermal vents, where superheated water, rich in dissolved minerals, billows out from cracks in the crust. These are the environments where many scientists believe life on Earth first emerged. Finding silica in Enceladus's plumes was direct evidence that the same kind of rock-water interactions, the same kind of hydrothermal activity, was likely happening right now on the ocean floor of this tiny moon. This meant Enceladus wasn't just a warm, salty ocean. It was a chemically active ocean, bubbling with the kind of energy and ingredients that could fuel microbial life. And the hits kept coming. Cassini's instruments also detected molecular hydrogen in the plumes. On Earth, molecular hydrogen is a key energy source for many chemosynthetic organisms. Life forms that don't rely on sunlight, but instead thrive on chemical reactions. The presence of hydrogen, along with carbon dioxide and methane, pointed to ongoing hydrothermal processes that could provide a continuous energy supply for potential microbes. This wasn't just a habitable environment. It was an environment where the metabolism of life could potentially thrive. The sheer volume of material erupting from Enceladus was staggering. The geysers were spewing water vapor and ice at an astonishing rate of about 200 kilograms, or 440 pounds, every single second. To put that into perspective, that's like an entire person's weight in water and ice being shot into space every 2 seconds. This wasn't a trickle. It was a torrent, a continuous outpouring from a hidden world. Scientists also estimated that Enceladus's global ocean is alkaline. with a pH somewhere between 11 and 12. That's comparable to a solution of ammonia or soapy water. While that might sound extreme to us, some Earth microbes thrive in highly alkaline environments, suggesting that such conditions wouldn't necessarily be a barrier to life on Enceladus. The ice shell itself, where these plumes punch through, is believed to be much thinner at the South Pole. While the average thickness across the Moon might be 20 to 25 kilometers, about 12 to 15 miles, at the Tiger Stripe fractures, it could be as thin as 1 to 5 kilometers, less than a mile to just over 3 miles. This relative thinness is what allows the powerful tidal forces, the same gravitational squeezing and stretching that warms Europa, to fracture the ice and create these spectacular eruptions. Tidal heating isn't just keeping the ocean liquid, it's driving the hydrothermal activity and literally blasting samples of that ocean out into space for us to collect. The aha moment was undeniable. We didn't have to figure out how to drill through miles of alien ice. We didn't have to send a submarine to the deepest, darkest trenches of an unknown ocean. The ocean came to us, presenting itself in a cascade of icy particles and chemical signatures. And then, in June of 2023, came perhaps the most compelling piece of the puzzle. Scientists announced the detection of phosphorus in Enceladus's plumes. Why is this so significant? Because phosphorus is the last of the 6 essential elements for life as we know it. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, often remembered by the acronym CNOPS. All 6 of these vital ingredients had now been confirmed to exist in Enceladus's ocean. The discovery of phosphorus was the final chemical confirmation that Enceladus's ocean has all the basic building blocks required for life. And not just present, but in surprising abundance. Phosphate concentrations in Enceladus's ocean are estimated to be at least 100 times higher than in Earth's oceans. Imagine that. An alien ocean, potentially richer in a critical life-giving element than our own. This wasn't just a habitable world. It was a super-habitable world, at least in terms of its chemical composition. The Cassini mission, which finally concluded its epic journey in 2017, with a deliberate plunge into Saturn's atmosphere to avoid any contamination of Enceladus or Titan, had revolutionized our understanding of the solar system. It showed us that habitability isn't just about distance from the sun or a planetary surface. It's about dynamic, internal processes, about the ceaseless dance of gravity, and about the unexpected ways that worlds can reveal their deepest secrets. Enceladus, this small, bright moon, had burst onto the scene, not with subtle hints, but with a dramatic, undeniable declaration. It had moved from a scientific curiosity to a prime target in the search for life, a testament to the fact that sometimes the most profound discoveries come from the most unexpected places. It taught us that the universe is far more imaginative than we are, and that the search for life is not just about looking, but about listening to the cries of distant worlds. And Enceladus had cried out a symphony of possibility. Enceladus had cried out a symphony of possibility. And the Cassini spacecraft, a silent, intrepid explorer hurtling through the Saturnian system, was perfectly positioned to hear it, to taste it. For decades, our search for life beyond Earth had been like listening for a whisper in a hurricane, or perhaps more accurately, like staring at a silent, arid landscape, hoping for a sign. But Enceladus didn't whisper. It roared. It sprayed a magnificent, continuous fountain of its deepest secrets into the vacuum of space. A plume of water vapor and ice grains erupting from deep fractures at its south pole, often called tiger stripes. These weren't just pretty light shows. They were a direct, open invitation from an alien ocean. Imagine for a moment The sheer audacity of it. Here was a tiny moon, barely 313 miles across, blasting hundreds of pounds of material per second from its interior, a natural cosmic geyser. This wasn't some subtle atmospheric efflux. This was raw, untainted ocean material, delivered straight to us, packaged for analysis. It was a gift from the cosmos, laid bare for our robotic emissaries. The Cassini mission, a marvel of engineering and human ingenuity, had been observing Saturn and its moons since 2004. In 2005, it made the initial, breathtaking discovery of these plumes. But seeing them was one thing. Understanding them, truly knowing what they were made of, that was another mission entirely. That required something extraordinary. It required Cassini to become, in essence, a robotic tongue. This wasn't a passive observation anymore. This was active, aggressive exploration. The mission scientists, led by visionaries like Dr. Carolyn Porco, leader of the Cassini imaging science team, realized they had a golden opportunity. If these plumes were indeed coming from a subsurface ocean, then flying through them would be like taking a core sample without ever having to drill. It was a shortcut to discovery, a direct conduit to an alien world that had never seen the light of day. The ice shell at Enceladus' south pole, where these plumes erupted, was believed to be as thin as 1 to 5 kilometers, making the ocean tantalizingly close to the surface. So, Cassini, with its array of sophisticated instruments, embarked on a series of daring flybys, deliberately plunging through these icy plumes. Picture it, this car-sized spacecraft, traveling at thousands of miles per hour, streaking through a cloud of icy particles and gas, each molecule a potential clue. It was a cosmic high-speed chase, a treasure hunt, where every particle collected was a piece of an alien puzzle. Its instruments weren't just cameras. They were like an exquisitely sensitive chemical laboratory on the move. The Cosmic Dust Analyzer, CDI, would catch individual ice grains, analyzing their composition. The Ion and Neutral Mass Spectrometer, INMS, would sniff the gases, identifying their molecular makeup. These weren't just data points. They were the ingredients of an alien recipe, being tasted and analyzed in real time. What did Cassini taste first? Salt water? That might sound obvious for an ocean, but consider the implications. This wasn't just pure water ice. The CDA detected tiny salt-rich ice grains. This meant the ocean wasn't just there. It was salty, just like Earth's oceans. It told us there was water-rock interaction happening beneath the ice, leaching minerals into the liquid. It suggested a dynamic, active environment, not a stagnant pool. You see, a salty ocean implies a connection to the rocky core, and that connection is absolutely critical for life. But saltwater was just the appetizer. The real banquet was yet to come. As Cassini continued its plunges, its robotic tongue detected something even more tantalizing: organic compounds. Now, let's be clear. Organic compounds don't automatically mean life. They're simply molecules containing carbon, often bonded with hydrogen, oxygen, and nitrogen. They are the chemical building blocks, the Lego bricks, from which life is constructed. Finding them in an alien ocean, alongside saltwater, was like finding a fully stocked hardware store in the middle of a desert. All the tools are there, just waiting for an architect. These weren't just simple carbon molecules. The NMS detected a wide variety of complex, heavier hydrocarbons, including benzene and propane. This suggested active, rich chemical processes, not just inert matter, stirring within the deep. Then came one of the first true aha moments, a discovery that sent ripples of excitement through the scientific community. Cassini's CDI detected microscopic grains of silica nanoparticles. Silica. Think sand. Think quartz. Think rocks. But these weren't just any silica particles. They were incredibly tiny, only a few nanometers in size, and critically, they were uniform in size. This uniformity told scientists they hadn't just been chipped off a rock. They had been formed under very specific, high-temperature conditions. The only known way to produce silica nanoparticles of this specific size and consistency in a water environment is through hydrothermal activity. On Earth, we find this at hydrothermal vents, deep on the ocean floor, where superheated water erupts from cracks in the crust. These vents are often called black smokers or white smokers due to the mineral-rich fluids they spew. They are teeming with life, forming entire ecosystems independent of sunlight, drawing energy from the chemical reactions between the hot vent fluids and the cold ocean water. The discovery of silica was the smoking gun for hydrothermal vents on Enceladus's seafloor. It meant that the rocky core of Enceladus wasn't inert. It was interacting with the ocean in a profound way, generating heat and creating the very chemical gradients that life on Earth thrives on. You see, for life to begin and be sustained, you need more than just water and organic molecules. You need energy. And hydrothermal vents provide that energy in spades, fueled by the tidal heating from Saturn's immense gravitational pull that flexes and kneads Enceladus's interior. This wasn't just a habitable environment. It was an energized environment, a cosmic battery. But Enceladus wasn't done revealing its secrets. Cassini also detected molecular hydrogen in the plumes. This was another huge piece of the puzzle. Molecular hydrogen is a powerful source of chemical energy for microbes on Earth, especially those living around hydrothermal vents. It's produced when hot water reacts with iron-rich rocks in a process called serpentinization. This reaction provides electrons, a fundamental requirement for metabolism. Finding H2 in such abundance was a direct indication of ongoing water-rock reactions, further reinforcing the idea of a chemically rich, energy-laden environment. It was like finding an open circuit, just waiting for life to plug in. With each new data point, the picture of Enceladus's subsurface ocean became clearer, more compelling. We had water, we had organics, we had an energy source in the form of hydrothermal vents, and we had chemical gradients. But there was still a missing piece, a fundamental ingredient often abbreviated by scientists as part of the CHNOPS elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 elements are considered the absolute necessities for life, as we know it, forming the backbone of DNA, RNA, proteins, and cell membranes. For a long time, while we had strong evidence for carbon, hydrogen, nitrogen, oxygen, and sulfur, phosphorus remained elusive. It's a critical component of ATP, adenosine triphosphate, the energy currency of cells, and the sugar phosphate backbone of DNA and RNA. Without phosphorus, life as we understand it simply cannot exist. Its absence was the nagging doubt in an otherwise incredibly promising scenario. Then, in June of 2023, nearly 6 years after Cassini's mission ended, a team of scientists meticulously reanalyzing decades of Cassini data with new techniques and insights finally made the groundbreaking announcement. They had found it: phosphorus. Specifically, they detected sodium phosphates in the ice grains of Enceladus's plumes. This wasn't just a minor discovery. This was the final missing piece of the CHNOPS puzzle. It was the ultimate smoking gun. With the detection of phosphorus, Enceladus's ocean now had confirmed presence of all 6 fundamental chemical ingredients required for life as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. All there, all confirmed. And the abundance of phosphorus was even more astounding. Estimates suggest that phosphate concentrations in Enceladus's ocean are at least 100 times higher than in Earth's oceans. Think about that for a moment. An alien ocean hidden beneath miles of ice not only has all the building blocks for life, but some of them, like phosphorus, are present in concentrations far exceeding what we find in our own life, teeming seas. This makes Enceladus not just a habitable world, but potentially a superhabitable world in terms of its chemical composition. So, what did Cassini's robotic tongue ultimately taste? It tasted a rich, complex chemical recipe. It tasted salt water, a vast liquid ocean, in contact with a rocky core. It tasted organic compounds, the very carbon-based molecules that form the foundation of biology. It tasted the telltale signs of hydrothermal vents, superheated water interacting with rock, providing energy and chemical gradients. It tasted molecular hydrogen, another potent energy source for microbial life. And finally, it tasted phosphorus, completing the set of 6 essential elements for life. It also tasted an ocean that is surprisingly alkaline, with a pH estimated between 11 and 12, comparable to a solution of ammonia or soapy water. This alkalinity, while different from Earth's oceans, is not necessarily a barrier to life. Indeed, some earthly extremophiles thrive in such conditions, particularly around certain types of hydrothermal vents. Each molecule detected was another ingredient confirming a potentially life-sustaining environment. This wasn't speculation anymore. This was direct chemical analysis. This was a direct sample of an alien sea, revealing a suite of conditions that, on Earth, are synonymous with life's origins and persistence. The evidence was overwhelming. Enceladus wasn't just an icy ball. It was a dynamic, active world, shouting its habitability into the cosmos. The sheer dedication and brilliance of the scientists and engineers behind the Cassini mission cannot be overstated. For decades, they designed, built, launched, and operated this incredible spacecraft, navigating it through the rings of Saturn, past its myriad moons, and finally, through the plumes of Enceladus. The data they collected and the subsequent meticulous analysis, some of it years after the mission concluded, represents one of humanity's greatest scientific achievements. It's a testament to patience, persistence, and the insatiable human drive to understand our place in the universe. This series of discoveries on Enceladus represented a profound paradigm shift in astrobiology. For so long, the focus had been on Mars, a world we could see, touch, and eventually land on. Mars offered tantalizing hints of ancient water, of a warmer, wetter past. But Enceladus and its Jovian cousin Europa offered something far more immediate, far more active. Present-day, vast, warm, saltwater oceans hidden beneath miles-thick shells of ice. These weren't just remnants of past habitability. These were ongoing sanctuaries for life. Right now, the idea that life could thrive in perpetual darkness, powered not by sunlight, but by the raw chemical energy of a watery, rocky interior, opened up our understanding of where life might exist. It expanded the habitable zone from a narrow band around stars to virtually anywhere there's enough internal energy and liquid water. Enceladus, this small, bright moon, became a beacon, a tangible proof of concept for the existence of ocean worlds as prime targets in our quest to answer the most profound question: are we alone? The dramatic plumes of Enceladus, continually broadcasting the chemical recipe of its hidden ocean, created an urgency. If this tiny moon was so generous with its secrets, what about Europa, the larger, more enigmatic moon of Jupiter, whose secrets were hinted at by more subtle, indirect clues? If Enceladus was actively advertising its potential for life, Europa was a silent, massive giant, holding its cards much closer to its chest. But the clues from Europa were equally compelling, even if they required more detective work. They too pointed to a vast, subsurface ocean, perhaps even grander in scale than Enceladus's. And just like Enceladus, Europa's ocean was kept liquid by the relentless gravitational dance of its host planet. While Enceladus provided the direct taste test, Europa's story began with a different kind of scientific sleuthing, a more subtle, yet equally powerful revelation about a hidden world. The stage was set for a deeper understanding of these ocean worlds, and the next chapter of our story takes us back to Europa, to the groundbreaking mission that first peeled back its icy veil, even if just a little. The first whispers of Europa's secret came not from a direct taste, but from a whisper in the dark, an almost imperceptible tremor felt across millions of miles of space. It was the mid-1990s, and NASA's Galileo spacecraft, a true pioneer, had arrived at Jupiter, beginning its long, arduous dance around the gas giant and its mesmerizing family of moons. For years, this tireless robotic explorer would send back tantalizing data, slowly, painstakingly, piecing together a picture of worlds utterly unlike our own. Among its most profound discoveries were the clues it gathered from Europa. Galileo didn't see plumes erupting like Enceladus. It didn't get to fly through a spray of alien ocean water. Instead, its most compelling evidence came from a subtle, yet undeniable distortion in Europa's magnetic field. Imagine a cosmic detective not looking for fingerprints, but for an invisible ripple in an unseen force. That's what Galileo's magnetometer did. As Europa orbited Jupiter, the moon passed through Jupiter's immense magnetic field. If Europa were just a solid block of ice and rock, it would interact with Jupiter's field in one predictable way. But Galileo detected something else entirely: an induced magnetic field, a secondary field generated within Europa itself. What could cause such a thing? The only explanation that made sense, the only one that fit the data, was a global ocean of salty, electrically conductive water hidden beneath miles of ice. Think of it like a giant battery, or more accurately, a massive swirling saltwater solution, acting like a conductor, creating its own weak magnetic field in response to Jupiter's powerful one. It was a profound, almost unbelievable revelation. This wasn't just a frozen rock. It was a deep, dark ocean, potentially containing more than twice the volume of all of Earth's oceans combined. And what kept this colossal ocean from freezing solid in the crushing cold of the outer solar system? The same incredible physics we saw at play with Enceladus: tidal heating. Imagine Europa, caught in an eternal tug-of-war, perpetually squeezed and stretched by the immense gravitational pull of Jupiter and its neighboring Jovian moons. This relentless kneading, this gravitational dance, generates immense friction and heat deep within Europa's interior, keeping that vast subsurface ocean liquid and potentially warm enough for life. It's a heat source independent of the sun, a geothermal furnace burning bright in the darkness, a truly alien hearth. Galileo's data painted a picture of an ice shell ranging from 6 to 20 miles thick, overlying an ocean that could be as deep as 60 miles. These were staggering numbers, transforming Europa from a mere point of light into a world of profound mystery and potential. And in a remarkable twist of scientific fate, decades later, in 2018, scientists re-examining Galileo's old data found new evidence suggesting the spacecraft might have unknowingly flown through a water plume erupting from Europa back in 1997. It was like solving a cold case, finding a crucial piece of evidence hidden in plain sight for 20 years. A hint that Europa might not be as silent as we once thought. But Galileo's mission, as groundbreaking as it was, could only offer inferences, powerful as they were. We had strong evidence of an ocean, but no direct taste, no definitive confirmation of its composition or the dynamics of its icy shell. We needed to move beyond the whisper in the dark and truly see what lay beneath. We needed a new kind of detective, one equipped with vision, capable of piercing through miles of alien ice. And that, my friends, brings us to the next giant leap in our quest. NASA's Europa Clipper mission. Launched in October 2024, the Clipper isn't just a spacecraft. It's an orbital detective, a cutting-edge laboratory designed to perform a detailed reconnaissance of Europa, specifically to investigate its habitability. Over the course of its mission, it will execute approximately 49 close flybys of Europa, dipping to altitudes as low as 69 miles, gathering an unprecedented wealth of data. This isn't a passive game of chance anymore. This is an aggressive, targeted investigation, an attempt to truly map the unseen. The Europa Clipper is equipped with an ingenious suite of instruments, each one a specialized tool in its orbital detective kit. Together, they give the Clipper what we might call X-ray vision and a supernatural sense of touch, allowing us to peer through Europa's icy veil like never before. It's designed to create the first detailed map of this hidden alien sea, to truly understand its dynamics, its potential for life, and to pave the way for humanity's next, even bolder steps. First, let's talk about that X-ray vision. This comes courtesy of the Reason instrument. Imagine shining a powerful flashlight through a dark, unknown substance. That's what Reason does, but with radio waves. It sends low-frequency radio waves directly through Europa's miles-thick ice shell. These waves then bounce back, reflecting off different layers within the ice, and crucially, off the interface between the bottom of the ice and the top of the ocean. By analyzing the timing and strength of these reflections, scientists can determine the precise thickness of the ice shell, not just in one spot, but globally. This isn't just about measuring thickness. It's about understanding the ice itself. Reason can detect variations in ice structure, identify warmer pockets within the ice, or even spot shallow subsurface lakes that might be embedded within the shell. Think of it as creating a geological cross-section of Europa's outer crust, revealing its hidden topography and composition. This X-ray vision is absolutely critical, because if we ever want to send a lander, or even more ambitiously, a cryobot, to melt its way through the ice, we need to know where the ice is thinnest, where the journey might be most feasible, and where the most interesting features might lie. It's like getting a comprehensive blueprint of a fortified vault before you even think about cracking it open. Then there's the Clipper's supernatural sense of touch, embodied by the IceMag instrument. Remember how Galileo detected that induced magnetic field, hinting at a salty ocean? IceMag is the next generation of that technology, designed to refine those measurements with incredible precision. A stronger induced magnetic field tells us the ocean is more conductive, meaning it's saltier. The way the field changes as the Clipper orbits also helps determine the ocean's depth and how that depth might vary across the moon. It's like feeling the pulse of a hidden heart, discerning its strength and rhythm without ever directly touching it. Furthermore, IceMag can detect localized magnetic anomalies that might indicate active plumes, just like the ones Enceladus famously erupts, or even suggest the presence of hydrothermal activity on the ocean floor. This instrument is our direct link to confirming and characterizing the very thing that makes Europa so compelling. Its vast, hidden, salty sea. But a detective needs more than X-ray vision and a supernatural touch. They need eyes to see the surface, ears to hear the sounds, and a nose to sniff out chemical clues. And Europa Clipper has those too. The EIS is the Clipper's Eye, a suite of high-resolution cameras that will map Europa's entire surface in stunning detail. While we have images from Voyager and Galileo, EIS will provide unprecedented clarity, allowing us to look for fresh cracks, intricate ridges, and those fascinating chaos terrains, areas where blocks of ice appear to have broken apart, shifted, and rotated, suggesting the upwelling of warmer material from below. These features are like breadcrumbs, pointing to areas of recent geological activity, which could be indicators of thin ice or even potential plume sources. It's about creating a detailed topographic map, a visual guide to Europa's dynamic icy skin, searching for any telltale signs of what lies beneath. To understand the chemical makeup of Europa, the Clipper carries a pair of sophisticated spectrometers. The MAGS will identify the composition of Europa's surface, looking for specific minerals, salts, and, most excitingly, organic compounds. These are the building blocks of life, and finding them on the surface, especially in areas of recent activity, would be a monumental discovery. Imagine finding the ingredients for a complex meal scattered on the kitchen counter. It tells you a lot about what might be cooking inside. Then there's MASSPEX. This instrument is designed to analyze tiny particles and gases. Its true moment to shine would come if Europa Clipper were to fly through one of Europa's suspected plumes. This would be Europa's equivalent of Cassini's taste test at Enceladus. MASSPEX could directly sample the contents of the ocean, analyzing the water vapor, salts, and organic molecules, providing a direct chemical signature of that hidden world. It's the ultimate sniffing out of clues, potentially confirming the presence of all the necessary ingredients for life. Much like the discovery of phosphorus in Enceladus's plumes solidified its status as a prime candidate. The Themis acts like a thermal camera, measuring heat radiation from Europa's surface. This is crucial for detecting warmer spots, which could indicate areas where the ice is thinner, where cryovolcanic activity is occurring, or where recent eruptions have deposited warmer material. It's like using a heat-sensing drone to find hotspots in a vast frozen landscape, guiding us to the most geologically active and potentially interesting regions. Finally, the PIMS will study the plasma environment around Europa. Jupiter's intense radiation environment is a harsh reality for any spacecraft operating in its vicinity, and understanding how this radiation interacts with Europa's surface and any escaping gases is vital for interpreting the data from other instruments and for planning future missions. It's about understanding the immediate cosmic neighborhood, a crucial piece of context for all the other observations. The combined power of these instruments is nothing short of revolutionary. No longer are we relying on subtle inferences or a single dramatic fly-through. The Europa Clipper is designed to systematically, meticulously, and comprehensively map this enigmatic moon. It's going to create a detailed weather map of Europa's ice shell, showing us where it's thick, where it's thin, where it's active, and where it's static. And simultaneously, through its magnetic readings, it will give us a kind of sonogram of the ocean beneath, revealing its depth, its salinity, and its hidden currents. This is the aha moment we've been building towards. We now have the technology, the ingenuity, and the scientific drive to move beyond just inferring the existence of an alien ocean. We are on the cusp of truly characterizing it, of understanding its dynamics, its potential for life, and its secrets from orbit. The Clipper is not just searching. It's laying the groundwork, drawing the treasure map for humanity's next, even bolder steps. Landers that will touch down on that alien ice melting probes, or cryobots, that could one day drill through miles of frozen crust, and autonomous submarines that could navigate the dark, abyssal plains of an ocean that has never seen the light of day. The question is no longer if we can explore these worlds, but when, and what profound truths they will reveal. If we find microbes there, what does that mean for our place in the universe? You know, for so long, the quest for alien life felt like a passive game. It was about pointing giant radio dishes at the stars, hoping to catch a whisper, a signal, a faint echo of intelligence from light years away. We were like fishermen, casting lines into an impossibly vast cosmic ocean, waiting, eternally waiting. But the profound discoveries at Europa and Enceladus have completely rewritten that script. They've transformed the search for life from a patient, distant vigil into an active, aggressive, and incredibly intimate pursuit. The real search isn't about listening anymore. It's about touching an alien world, tasting its secrets, and ultimately drilling through its frozen shell to find what lies beneath. The Europa Clipper, as incredible as its mission is, represents just the first page of this exhilarating new chapter. It's our orbital scout, our cosmic cartographer, diligently drawing the maps and taking the crucial measurements from above. It will use its sophisticated ice-penetrating radar, the Reason instrument, to peer through miles of ice, searching for water pockets and subsurface lakes, creating a detailed sonogram of the ocean beneath. Its magnetometer will precisely measure Europa's induced magnetic field, refining our understanding of the ocean's depth and salinity, an echo of the groundbreaking data provided by Galileo decades ago that first hinted at this hidden world. But the true frontier, the most profound mystery, lies not in the vast distances between worlds, but in the few brutal miles beneath their icy crusts. This, my friends, is what we call the final frontier within. And conquering it demands an engineering leap so monumental, it will redefine what we believe is possible. Imagine, if you will, the sheer audacious challenge. You have a world like Europa, an alien jewel orbiting Jupiter, shrouded in an ice shell that's estimated to be anywhere from 10 to 30 kilometers thick. That's 6 to 20 miles of solid, unforgiving ice, a colossal barrier. Or Enceladus, Saturn's tiny active moon, with an ice shell averaging 20 to 25 kilometers in thickness, though it may thin dramatically to just 1 to 5 kilometers at those dynamic South Pole tiger stripe fractures where its geysers erupt. We're talking about depth that utterly dwarf the deepest trenches of Earth's oceans. This isn't just cold ice. This is ice under immense, crushing pressure in the vacuum of space, bombarded by intense radiation. It's a barrier unlike any we've ever faced, a formidable frozen fortress protecting a global sea. So how do you get through it? How do you reach an ocean that has never, in its entire existence, seen the light of day? An ocean that holds the potential answers to humanity's oldest, most profound questions. You send in the cryobots. Picture this with me. Future probes will be like robotic seeds planted on that alien ice. They won't land with a gentle thud and roll away. They'll settle in for the long haul, designed for a profoundly different kind of journey. These aren't the quick, flashy rovers we've sent to Mars, darting across dusty plains. These are patient, tenacious machines, built for a mission, measured not in days or weeks, but in years, perhaps even a decade, of constant, relentless operation. Their singular, audacious mission: to slowly, methodically melt their way down through the darkness, mile after frozen mile. A cryobot is, in essence, a highly sophisticated self-powered ice-melting probe. Its core principle is elegant in its simplicity, yet incredibly complex in execution. It generates heat, warming the ice directly beneath its base, turning it into liquid water. As the ice melts, the probe slowly sinks, displacing the newly formed water, which then refriezes above it, sealing its path and preventing it from floating back up. It's a bit like a reverse burrowing worm, methodically carving its own tunnel and leaving a robust, frozen channel in its wake. This isn't a quick sprint to a destination. It's a marathon through an alien geological layer cake, a meticulous, deliberate descent into the unknown. The engineering challenges inherent in such a mission are absolutely staggering, stretching the limits of our technological prowess. First, there's the critical issue of power. You're operating far from the sun, so conventional solar panels are utterly useless. These probes will demand advanced radioisotope thermoelectric generators, or RTGs, similar in concept to those that powered the venerable Cassini mission or the Mars Curiosity rover, but far more robust, efficient, and designed to last for an unprecedented duration, years, perhaps even a full decade, in continuous, uninterrupted operation. They'll be slowly, steadily converting the heat generated from the natural decay of plutonium into the electricity required to melt the ice and power their intricate array of scientific instruments. It's a testament to the power of atomic decay, harnessed for exploration. Then there's the monumental task of navigation. As the cryobot descends, it's operating in a realm of absolute unyielding darkness, miles beneath the surface. How do you ensure it stays precisely on course, avoids unexpected obstacles, and doesn't become hopelessly stuck in a crevasse or a pressure ridge within the ice? Advanced sonar systems, constantly mapping the ice ahead and around it, combined with sophisticated internal navigation units, will be absolutely crucial. Imagine trying to navigate a vast, shifting mountain range blindfolded, except this mountain is constantly reforming and closing around you as you move. The probe must autonomously sense its environment, identify potential hazards, and plot the safest, most efficient path downward. And the pressure, as the cryobot melts deeper and deeper, the immense weight of those miles of ice above it increases exponentially, reaching pressures that would instantly crush a conventional submarine. The cryobot's hull, therefore, will need to be forged from incredibly robust, exotic materials engineered to withstand these unimaginable forces, all while maintaining its internal warmth and protecting its delicate, sensitive electronics. It's not just a probe. It's a tiny, self-contained fortress, meticulously designed to endure and slowly descend into an abyss of crushing force and frigid cold. Communication presents another formidable hurdle. How do you talk to a probe that is miles under ice, shielded by a thick, electrically conductive layer of water? The current thinking involves a groundbreaking system of repeater beacons. These would be small, robust data relay units that the cryobot would deploy at carefully calculated intervals as it descends. These beacons would remain frozen permanently in the ice, creating a vital communication chain, a digital breadcrumb trail leading back to the surface. There, a dedicated lander would collect the data and relay it to orbiting spacecraft, and eventually, after an immense journey across the solar system, back to us, here on Earth. Imagine the suspense, years of silence, punctuated by brief, precious data packets, confirming the descent, the health of the probe, and the mysterious conditions of the ice. Each message a triumph of engineering and perseverance. And let's not for a moment forget the paramount importance of planetary protection. We are talking about potentially pristine alien environments, worlds that have been untouched by any form of terrestrial life for billions of years. Any probe we send must be sterilized to an almost unimaginable degree, far beyond hospital standards, to prevent even the slightest possibility of contaminating these worlds with Earth microbes. The last thing we want, after all this effort, is to discover alien life, only to realize, with a crushing sense of irony, that it's a bug we inadvertently brought along for the ride. The Cassini mission, in its awe-inspiring grand finale, was deliberately plunged into Saturn's atmosphere, sacrificing the spacecraft, precisely to avoid any chance of contaminating the pristine oceans of Enceladus or Titan with earthly biological material. That's how profoundly seriously we take this responsibility. The journey itself, through those miles of alien ice, could realistically take years. Years of patient, methodical melting, each centimeter a hard-won victory against an unforgiving environment. But then one day, after what would feel like an eternity, to the scientists and engineers waiting back home, the cryobot would break through. It would pass through the final, thinnest layer of ice. And that, my friends, is the germination. It would emerge, not into the vacuum of space, but into an entirely new, completely alien ecosystem. An ocean that has been dark and untouched since before life began on Earth. That pivotal moment is when the next, even more breathtaking phase of exploration begins. The deployment of autonomous submarines. Imagine being there virtually, as that cryobot finally reaches the liquid ocean. The robotic seed has germinated, fulfilling its arduous missions. From its belly, or perhaps deployed alongside it from the surface, would emerge a sleek, powerful autonomous underwater vehicle, an AUV. This submarine would be humanity's first true direct explorer of an alien sea. These submarines would be unlike anything we've ever conceived for space before. They'd be custom designed to thrive in crushing pressures and absolute darkness, navigating an ocean that has never known the faintest glimmer of sunlight. They'd be equipped with advanced sonars to map the seafloor with unprecedented detail, high-resolution cameras to capture images of the unimaginable, and sophisticated chemical sensors to taste the water directly, just as the Cassini spacecraft so famously tasted Enceladus's plumes from orbit. And what might they find down there, in those abyssal depths? Think back to the groundbreaking discoveries at Enceladus. Cassini didn't just find water, it found salt water, indicating a global ocean. It found organic compounds, the very building blocks of life. Crucially, it found silica nanoparticles, a clear, unmistakable signature of hot water interacting with rock, providing compelling evidence for active hydrothermal vents on the ocean floor, much like those found in Earth's deep oceans. And then, in 2023, the final incredible piece of the puzzle fell into place. The detection of phosphorus, the last of the 6 essential elements for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, or CHNOPS, to be unequivocally confirmed in Enceladus's plumes. This profound discovery means that Enceladus's ocean possesses all the fundamental chemical ingredients for life as we know it, delivered by the kind of energetic hydrothermal vents that many scientists believe may have spawned life on Earth itself. The ocean there is even estimated to be alkaline, with a pH between 11 and 12, comparable to soapy water, and surprisingly, phosphate concentrations are at least 100 times higher than in Earth's oceans, a truly remarkable abundance for this life-critical element. So, our autonomous submarines would be specifically programmed to search for those very vents. On Earth, these deep-sea hydrothermal vents are teeming with incredibly diverse life, thriving in complete darkness, powered not by sunlight, but by chemical energy through a process called chemosynthesis. They are vibrant oases in the otherwise barren abyss, supporting entire ecosystems. Could the same be true on Europa or Enceladus? The possibility is breathtaking. The oceans themselves are immense, presenting an exploration challenge of truly cosmic proportions. Europa's subsurface ocean, for instance, is estimated to contain 2 to 3 times the staggering volume of all of Earth's oceans combined. And it could be up to 100 kilometers, 60 miles, deep. Imagine the sheer scale of exploration that would be needed. Our submarines, despite their advanced capabilities, would be like tiny specks in an alien Pacific, meticulously charting the unknown. One sonar ping at a time, they would be actively looking for signs of active geology on the seafloor, potential volcanic activity, deep fissures, and, most importantly, plumes of hot, mineral-rich water emanating from those hydrothermal vents. They'd be sniffing for subtle chemical gradients, for unusual concentrations of organic molecules, for anything that whispers of metabolism, of biological processes that might be operating in the dark. They'd be searching for microbes, for communities of life forms, utterly unlike anything we've ever encountered, organisms that have evolved in complete isolation from our own biological lineage. The navigation for these submarines would be entirely autonomous, based on highly sophisticated pre-programmed scientific objectives and real-time data analysis. There would be no human pilot down there, no remote control from Earth, with light-speed delays that would render direct control impossible. These machines would be true pioneers, making their own decisions, adapting to an environment we can only begin to imagine. A world of perpetual night and immense pressure. The greatest challenge in space exploration may not be the vast, mind-bending distance between planets, but the deceptively simple depth of a few miles of alien ice. Conquering it is not just an engineering feat. It is the next giant leap for humanity. It's a profound testament to human ingenuity, to our relentless drive to understand our place in the cosmos, to push the boundaries of what is possible. It's an investment of decades, of billions of dollars, of untold human effort, all focused on piercing a frozen veil to peer into an unknown sea. And if we succeed, if our robotic seeds germinate and our autonomous submarines send back images, chemical signatures, or even direct samples confirming microbial life in those sunless depths, the ramifications would be utterly profound, shaking the very foundations of our scientific understanding, our philosophies, and our culture. It would mean that life isn't a unique, improbable accident that happened only once, here on Earth. It would mean that given the right conditions, liquid water, chemical energy, the essential building blocks, life might be common, perhaps even abundant, throughout the universe. It would irrevocably transform our cosmic perspective, moving us from feeling utterly alone to being part of a potentially vast, vibrant, living cosmos. It would challenge our philosophies, our religions, our very definition of what it means to be human in a universe teeming with other forms of existence. Are these alien microbes our distant cousins, a shared evolutionary spark from the same cosmic dust? Or are they completely unrelated, born from a separate genesis, a second independent origin of life that would prove the universe is truly fertile? The questions would multiply exponentially, each one more profound, more paradigm-shifting than the last. This isn't just science. It's an adventure of the soul, a journey into the deepest parts of our collective curiosity. It's humanity, reaching out across billions of miles and then down through miles of ice to shake hands with a neighbor we never knew we had. It's the ultimate act of discovery, a journey not just to another world, but to a deeper understanding of ourselves, our origins, and our destiny. The journey through the ice, the exploration of the dark oceans. These are not just engineering challenges. They are a reflection of our deepest curiosity, our primal need to know if we are truly alone. And the answers once found will forever change our story. This is the ultimate frontier, not the stars above, but the oceans within. And we are ready to dive in. What will those dark, hidden waters reveal about life itself and our singular place in this incredible universe. If you're as captivated by these cosmic mysteries as we are, make sure to hit that subscribe button. Join us on Celestial Enigmas as we continue to explore the breathtaking wonders and profound questions of our universe. The search for life beyond Earth, for generations, was a passive whisper into the cosmic void, a hopeful ear pressed against the universe, waiting for a signal. We scanned the stars, our gaze fixed on distant suns, imagining civilizations broadcasting their existence across light years. But what if the answer wasn't a broadcast from afar, but a secret held close, beneath our very noses, shrouded in ice and darkness? What if the most profound discovery of our age wasn't about listening, but about reaching? We've spent decades looking for life on arid, sun-baked surfaces like Mars, envisioning tiny green men, or at least hardy lichens, clinging to red rocks. We were looking in the wrong place. We were playing a game of chance, hoping that life, in all its improbable glory, would announce itself or leave obvious clues on exposed landscapes. But the universe, it turns out, is far more subtle and far more astonishing than we first imagined. The most promising candidates for extraterrestrial life aren't red deserts, but vast, warm, saltwater oceans hidden beneath miles-thick shells of alien ice. These are the ocean worlds of Europa and Enceladus, and they represent a paradigm shift in our quest for cosmic companionship. This isn't a passive game of chance anymore. The real search for alien life is active, aggressive, and much closer to home. It involves building incredible machines, born of human ingenuity and sheer will, designed to drill through miles of alien ice. It means pushing the boundaries of engineering to reach the single most promising environments for life we have ever discovered. Oceans that have never seen the light of day. This isn't just science. It's a philosophical quest, a journey to find what could be a second, independent origin of life in the cosmos. It would be like discovering a completely separate book of Genesis in the cosmic library. It proves the story of life is not a unique novel, but a genre. Think about it. For centuries, our understanding of life has been singularly defined by Earth. Every organism, from the smallest microbe to the largest whale, traces its lineage back to a common ancestor, a single spark that ignited in some primordial soup billions of years ago. Our biology, our very essence, is a product of this one precious story. But what if there's another story, a completely different narrative of creation, playing out in the deep, dark, and utterly alien waters of another world? What would that mean for us? For our understanding of life itself, for our place in this vast, often silent universe? Our journey to this profound realization began quietly, with a spacecraft named Galileo. Back in the late 1990s, Galileo orbited Jupiter, dutifully collecting data from the gas giant and its many moons. Among them was Europa, a world wrapped in a gleaming, cracked shell of ice. Europa captivated scientists with its smooth, almost billiard ball-like surface, crisscrossed with tantalizing lines and fractures that hinted at geological activity below. The twin Voyager spacecraft in the 1970s had given us our first close-up images, revealing this surprisingly smooth surface with few craters, a sign of a geologically young and active world. But it was Galileo that provided the first strong evidence for something truly astonishing: a subsurface ocean. How did it do it? Through the subtle dance of magnetic fields. Dr. Margaret Keivelson, a key scientist on the Galileo mission, and her team used the spacecraft's magnetometer to detect an induced magnetic field around Europa. This wasn't Europa's own magnetic field, but one generated by its interaction with Jupiter's immensely powerful magnetic field. This induced field was the smoking gun, suggesting a global ocean of salty, electrically conductive water hidden beneath the moon's icy crust. It was a brilliant piece of cosmic detective work, inferring the presence of an entire ocean, not by seeing it directly, but by observing its invisible electromagnetic footprint. The sheer scale of this hidden ocean is mind-boggling. Scientists estimate Europa's subsurface ocean contains 2 to 3 times the volume of all of Earth's oceans combined. Imagine that, a colossal reservoir of liquid water, more than humanity has ever known, locked away beneath miles of ice. That ice shell itself is a formidable barrier, estimated to be anywhere from 10 to 30 kilometers, about 6 to 20 miles, thick, overlying an ocean that could be up to 100 kilometers, 60 miles deep. For context, that ice shell is around 10 times thicker than the deepest point in Earth's ocean. The incredible thing is how this ocean stays liquid in the deep cold of the outer solar system. The answer lies in a phenomenon called tidal heating. It's a cosmic dance, a gravitational tug-of-war. Jupiter, the colossal giant, and its neighboring moons like Io and Ganymede constantly squeeze and stretch Europa as it orbits. This relentless flexing and kneading of Europa's interior generates immense friction, creating enough heat to keep that vast ocean liquid, potentially warm, and capable of supporting life. And the clues keep coming. In 2018, scientists reanalyzed 2-decade-old Galileo data, playing cosmic cold case detectives, and found new evidence for water plumes erupting from Europa, suggesting the spacecraft may have unknowingly flown through one back in 1997. More recently, the powerful James Webb Space Telescope detected carbon dioxide on Europa's surface, concentrated in a geologically young region. This suggests that the carbon dioxide likely originated from the internal ocean and was recently deposited, adding another tantalizing piece to the puzzle of Europa's habitability. But while Europa whispered its secrets, another ocean world, smaller but far more boisterous, began to shout. Enter Enceladus, a tiny moon of Saturn, discovered by the Cassini probe in 2005. Cassini, a joint mission by NASA, ESA, and ASI, transformed our understanding of the Saturnian system during its incredible 13-year journey from 2004 to 2017. It was in 2005 when Cassini made a discovery that would forever change the search for extraterrestrial life. Geysers erupting from the south pole of Enceladus. This wasn't an induced magnetic field or subtle surface features. This was direct, undeniable evidence of liquid water actively spewing into space. Imagine the sheer drama of that moment for the Cassini team. Here was a moon, barely 500 kilometers, 310 miles, across, about the width of Arizona, actively venting vast plumes of water vapor and ice grains from distinctive tiger stripe fractures at its south pole. These geysers erupt at an astounding rate, about 200 kilograms, 440 pounds, of material per second, traveling at speeds of approximately 400 meters per second, 800 miles per hour. This isn't just a trickle. It's a cosmic cry, a direct invitation to sample its hidden depths, and Cassini did exactly that. In a series of daring flybys, the spacecraft plunged directly through these plumes, its instruments tasting the contents of the ocean below. It was a eureka moment for the ages. The analysis of these plume samples revealed a veritable cocktail of ingredients crucial for life. Saltwater organic compounds, the building blocks of life, and perhaps most tellingly, silica nanoparticles. The presence of silica, a form of rock, was the smoking gun for active hydrothermal vents on Enceladus's ocean floor. On Earth, these deep-sea hydrothermal vents, fueled by the interaction of water with hot rock, are thought to be the very cradle of life, teeming with unique ecosystems, thriving in perpetual darkness, independent of sunlight. The discovery of a similar environment on Enceladus, billions of miles away, was a truly profound connection. The story of Enceladus's ocean continued to unfold like a gripping scientific detective novel. Further analysis of the plumes confirmed the presence of molecular hydrogen, another key energy source for potential life. And over time, scientists painstakingly identified all 6 essential elements for life as we know it on Earth. The CHNOPS elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. But the final piece of this puzzle, phosphorus, proved elusive. It's a vital ingredient, forming the backbone of DNA and RNA, and a crucial component of cell membranes and bones. For years, models were divided on whether Enceladus's ocean could harbor significant quantities of it. Then, in June 2023, based on a meticulous re-examination of Cassini data, scientists announced the detection of phosphorus in Enceladus's plumes. It was the last crucial element confirmed, solidifying Enceladus as an incredibly promising candidate for habitability. And not just present, but abundant. Phosphate concentrations in Enceladus's ocean are estimated to be at least 100 times higher, and possibly even 1,000 times higher, than in Earth's oceans. This surprising abundance of a life-critical element strengthens the case for habitability immensely. Furthermore, Enceladus's ocean has been found to be alkaline, with a pH estimated between 10.1 and 11.6, comparable to soapy water. While challenging for some Earth life, some microbes on our own planet thrive in such alkaline conditions. This tiny moon, barely a speck in the vastness of the Saturnian system, is actively advertising its potential for life, a cosmic billboard declaring its secrets to the universe. Its average ice shell thickness is around 20 to 25 kilometers, but critically at the South Pole where the plumes erupt, it may thin to as little as 1 to 5 kilometers, making that hidden ocean tantalizingly close to the surface. These discoveries shift the entire conversation. We're no longer just wondering if life exists elsewhere. We're pointing to specific locations with specific chemical signatures where the conditions appear not just favorable, but strikingly similar to where life began on Earth. This moves the search from abstract speculation to tangible exploration. This is why the search is no longer just about science, but philosophy. Discovering a second, independent origin of life would fundamentally change our cosmic perspective. It would be like finding a completely separate book of Genesis in the cosmic library. It would prove that the story of life, this miraculous, improbable phenomenon, is not a unique novel, a one-off event confined to our pale blue dot, but a universal genre, a common theme woven into the fabric of the cosmos. It would mean that life isn't an anomaly, but perhaps a natural, inevitable outcome when the right conditions coalesce. So, what are the next steps in this monumental quest? We are already building the tools and have chosen our destination. The Europa Clipper mission, NASA's next major endeavor to an ocean world, launched on October 14, 2024. This incredible spacecraft is currently on a 1.8 billion-mile journey, making gravity-assist flybys of Mars in March 2025 and Earth in December 2026, before arriving at Jupiter in April 2030. Europa Clipper won't orbit Europa directly, but will instead orbit Jupiter and perform approximately 49 close flybys of Europa over its 3.5-year mission. These flybys will take it to altitudes as low as 25 kilometers, about 16 miles, above the Moon's surface. The suite of instruments on board Europa Clipper is a marvel of modern engineering, designed to essentially X-ray the Moon from orbit. The radar for Europa assessment and sounding, ocean to near surface, or REASON, is an ice-penetrating radar. It will probe Europa's icy shell, searching for reflections from the subsurface ocean, and mapping its structure and thickness, even looking for subsurface lakes. The Europa Clipper magnetometer, EALTOM, will confirm the ocean's existence, measure its depth and salinity, and determine the ice shell's thickness, building on Galileo's foundational work. Other instruments, like the Europa Imaging System, EIS cameras, will capture high-resolution images, while the mass spectrometer for planetary exploration, Europa, MASSPEX, will analyze gases in Europa's faint atmosphere and any potential plumes, offering a taste of Europa's composition, much like Cassini did for Enceladus. But the ultimate goal, the true plunge into the unknown, lies with future mission concepts. Imagine the engineering prowess required to send a cryobot, an ice-melting probe, through miles of solid ice. This wouldn't be a quick journey. It could take years, a slow, patient descent into the crushing darkness. We picture it, a glowing, heated probe, meticulously melting its way downward, enduring immense pressure, navigating potential hazards within the ice, its sensors eagerly scanning for the transition from solid to liquid. And then, the breakthrough, a shimmering alien ocean, never before touched by sunlight. And what then? Autonomous submarines. These intrepid robotic explorers would navigate the sunless seas of Europa or Enceladus, silently gliding through waters potentially richer in phosphorus than Earth's, powered by the very chemical energy of hydrothermal vents. They would explore alien seafloors, searching for the telltale signs of life, perhaps even capturing samples of microbial communities that have evolved in complete isolation from our own biosphere. These are not distant dreams. These are blueprints being drawn today, challenges being tackled by brilliant minds, driven by that same ancient human curiosity that compelled us to gaze at the star. The journey to these ocean worlds is more than a scientific expedition. It's a re-evaluation of our cosmic identity. If we find microbes there, thriving in those dark, hidden sanctuaries, it won't just be an answer to the question, "Are we alone?" It will be an answer to a deeper, more profound question about life itself. It will force us to confront the possibility that life is not a unique phenomenon, but a fundamental characteristic of the universe, emerging wherever the conditions allow. The final question is no longer if we can find an answer, but are we ready for what that answer means for our place in the universe? Are we ready to rewrite our own book of Genesis, to accept that our story, while precious and unique, might be just one of countless others, all unfolding in the vast, wondrous cosmic library? We stand on the precipice of a discovery that could redefine everything. The tools are being built, the destinations are chosen, and the human spirit of exploration burns brighter than ever. What secrets will these hidden oceans reveal? And how will we, as a species, respond to the ultimate revelation that we are, after all, not alone?